now we want to get into what would be a good choice of pulse shape. If in theory I can use any pulse shape I want, in practice I'm going to use a shape that is convenient for me or has some good properties for me. And one of the definitions of what would be a good property in a sampling receiver is that the pulse should be 0 at all sampling times except 0. I'm not talking about intersymbol interference now. I'm just talking about sending a pulse train. If I send a pulse train, I want to know that when I sample and I want to look at a particular pulse, I'm only going to get non-zero input from the pulse that I'm sampling at that instant, and that all the other contributions from other pulses, previous, later, they all contribute 0, and they're not part of my decision statistic. So that is the definition of what we call a Nyquist pulse. Normally, if we had a pulse that was greater duration than the time of 1 bit, we would be worried that even without the filtering effect, we would indeed be creating intersymbol interference. But if we follow this definition and only consider Nyquist pulses, then I will not get any intersymbol interference, even though the pulse has maybe infinite duration, but at the very least is not confined to 1 bit time. So there is overlapping of pulses, not due to any filtering effects now. I have overlapping of pulses because that's how I design my pulses. But the overlapping is controlled. It's controlled in such a way that I choose pulses that pass at 0 every time we go through the sampling time, except of course for the main lobe of the bit. So there are many examples of Nyquist pulses, and of course the most obvious example is an RZ pulse, a rectangular pulse. A rectangular pulse is 0 outside the bit interval, so of course at all the other sampling times it is also 0. The sync function is a function that also goes through 0 periodically at every bit interval. So that would be a valid Nyquist pulse. There's also a pulse called a raised cosine pulse, which is one that is commonly used in the laboratory because it has many nice features, and it is, so let's say for now, another example of a Nyquist pulse. I think you've probably heard of a root raised cosine pulse, and that's not actually a Nyquist pulse. It's an abuse of the vocabulary a little, but it's related to the raised cosine pulse, which is a valid Nyquist pulse. So let me just use the term about the ideal Nyquist pulse, which we hear sometimes. And the ideal Nyquist pulse has the form of a sync function in the time domain. And in the frequency domain, it has a rectangular frequency response. Signal in the time domain is on the right. It's a signal which takes the form of a sync. So it is every signal sent, every bit sent actually has infinite time duration. You have to be in the lab a long time for this one. And however, every time sampling interval, it will pass by 0. And if we look in the frequency domain, it has a very, very small bandwidth. In fact, it's called ideal because among all of the Nyquist pulses, it has the smallest bandwidth. It is the most spectrally efficient of all Nyquist pulses. So it has some other bad qualities, but one good quality it has is that it's very spectrally efficient, and that's why it has gained the name of the ideal Nyquist pulse. I talked about spectral efficiency, and of course spectral efficiency is the ratio of the transmission rate divided by the bandwidth occupied in order to achieve that. So if I hold constant the transmission rate for all Nyquist pulses, their bandwidth is different, and this bandwidth for the ideal Nyquist pulse is the smallest one, and this is the most spectrally efficient. So I said that we have a family of Nyquist pulses that we can use, and what do we want to achieve? Why do we have such a wide selection of pulses? Well, we want to trade off to try and get something that is bandwidth efficient, but can also help us avoid ISI due to filtering effects. And of course, bandwidth efficiency will do that. It'll help us avoid ISI. Something relatively easy to implement and something that's robust to timing errors. And I'll show you how these nice pulses can achieve them. So remember, pulses which are limited to TB they're wide in bandwidth. If you have time limited, that means they're wide in bandwidth. And if I have a really wide bandwidth, I'm going to run into trouble with the intersymbol interference. So that's why I don't like to use the rectangular pulse if I have to, because that's more vulnerable to ISI just because it takes up a lot more bandwidth. If I use Nyquist pulses that have a time duration greater than TB, if I have no pulse spreading, then there's no ISI, since these Nyquist pulses pass to 0 the sampling time. And they can be narrow band. We saw that the ideal one is very narrow band, so ISI will be less likely because I'm taking up less space in the frequency domain. Historically, optical channels were very, very wide band, and that we didn't worry about these spectral efficiency. But now as we're going into more dense packing of spectrum, having spectrally efficient pulses is more important. And also, they can be more robust to timing errors if we do our choice correctly, which can also be very helpful in the system, and I'll show you about that trade-off. So let's look at the raised cosine. I have the definition here. These are programmed into MATLAB already. It's programmed into OptiSystem. But the important thing I just want to show you in these equations is there's a sinc function and there's a roll-off factor. And the roll-off factor is a factor that we can tweak in order to trade off different characteristics of this pulse in order to favor some characteristics over others. For instance, spectral efficiency, because we can see the R is directly in the equation for the frequency support of the signal. So here is a graph. Left is the frequency response, right is the pulse shape, and they're for different roll-off factors. Roll-off factor of 0 is the ideal Nyquist pulse, and it has the smallest bandwidth. As you can see, it's the rectangle. And if you look in the time domain, it's the one with the biggest side lobes. So the good effect is that it's spectrally efficient. The bad effect is it has very large side lobes. Why are large side lobes bad? Well, if I do have some intersymbol interference, that means that it's probably going to be greater because I have large side lobes. Also, if I just have timing error, so that I'm sampling not at exactly a multiple of the bit time, but someplace off, the larger the side lobe, the larger the error is going to be due to the contribution from other pulses. This just shows you the pulse shapes, what they look like for different roll-off factors. In black is the R equals 0 for rectangular pulses, and then as we go to others. Again, if we're trying to achieve these RC pulse shapes, of course, they have infinite time support, which we cannot deal with in the lab. So, of course, we're going to have to truncate and delay in order to create a pulse that can be transmitted. Here's an example of a pulse that's truncated after 4 side lobes, and it has to introduce a delay of 3 bits in order to realize the shaping filter for these pulse shapes. So I said that we're going to optimally use a match filter at the receiver, and if I want to have the good effects of my received pulse post-filtering looking like an RC form, then what I have to do is use the square root of that frequency response in the transmitter and the square root of that frequency response in the receiver. And when these two are multiplied together, assuming I have a channel which is all pass and perfect, then the ultimate effect of these two filters would give me the cumulative effect of a raised cosine filter. So that is why we see the root raised cosine filter. In order to have the good effects, for instance, robustness to timing and other effects, we would use RRC instead of an RC filter. So it's not really Nyquist, but it's pretty close anyway, and has the effects we're looking for. Okay, just finish up this part of the discussion with the illustration about an NRZ rectangular pulse. This is the spectral density of the pulse, and on the left there's no noise, on the right there is noise. And then if I fix the transmission rate, but instead of using a rectangular pulse, I use instead an RC pulse with a 30% roll-off factor, I can see the new shape here, which is much more spectrally efficient and much better job at rejecting noise. You can see the bandwidth is much smaller. In the case of the NRZ pulse, it's 2 times the transmission rate, and in the case of the 30% roll-off factor, it's 1.3, so it's saving you, and that means that there's less noise getting through in your system as well.